Okay, good afternoon. We'll start, please. Okay, maybe you have seen the message on talk or on live session today, so please be quiet. Okay. So this week we finished the third session with Mr. Scherer. Okay, you've seen the kinematic analysis, three steps of the kinematic analysis. Before to start some exercise on this, I will show you some elementary technological function. Okay, like this, you will be able to read a technical ring, understand the function of this different part, and also today see the different part. Okay, I bring you some of parts. But we will see the different function of a mechanism and how to realize three different joints: complete, revolute, and sliding joint. Okay, so the complete joint, guiding in translation and guiding in rotation for the second one. Okay. The objective of the elementary function is to find in standard component the way to realize a real function. Okay, or to realize in concrete a complete joint or a revolute joint or a sliding joint. Okay. We'll use standard components to reduce the cost and to reduce the time for the study of the mechanism. Okay? In first year, your job is to be able to read a technical drawing, to realize the kinematic analysis. Okay? I will just show you the different functions, how they are realized, but it's not necessary to know how to realize them. You just have to know to be able to read them on a technical drawing. Okay? So on a mechanism, we'll divide the complete mechanism into different functions and also sub-functions. Okay, for example, on a body, we can divide in different subsystems, under, seat, brake system, chain, etc., the frame, etc., etc. In one subsystem, we can explain all the functions. For example, in the wheel subsystem, we can divide the wheel into the tire, the rim. The rim could be divided in the hub, the rim, spoke, etc., etc. Okay? All mechanisms are divided in different functions. Okay? In general, we divide a mechanism in two great functions, electrical and mechanical. In mechanical design, we only study the mechanical function. Okay? Main function of mechanical design is to connect different parts, is to realize joints between the different parts. Okay? So first function, joint function. One student, please. Hello. Hurry up, please. Sorry. So the first is to connect parts each other with the joint function, or to realize a complete joint, a revolute joint, and a sliding joint, or a specific joint. Okay? Is the subject of the lesson of today. Here also, guiding function is to reduce the friction between different parts. Okay? We'll also see this today. Guiding in translation, guiding in rotation. Okay? Two other complement function. In general, in a mechanical mechanism, we need to lubricate the system. Okay, we'll add oil to reduce the friction between the parts to avoid problem of temperature. Okay, so we add oil inside of the mechanism to reduce all of this. So we need a lubricate function, and also, if we add oil, we need a sealing function to avoid to put oil outside of the mechanism. Okay. We'll see lubricate and sealing on the second semester. Okay? How to choose a joint inside the joint function? I have to choose different points. Okay? The joint, is it rigid or elastic? Okay? Is it complete? To realize the complete joint without any degree of freedom, or maybe I need one or more degree of freedom. One rotation, revolute joint. One translation, sliding joint. Okay? The joint, is it direct or indirect? A direct contact between the different parts, or maybe use an intermediate part to realize the joint. For example, a ball bearing in a revolute joint. Okay? For complete joints, or also for turning and sliding joint, the joint realized, is it mountable, dismountable, is it necessary or not? Okay? So we'll find all the standard technological function to realize all these functions and to choose the correct function in function of my use. Okay? I'll give you the pages for this in the technical pocket guide, but it's the main part of the technical pocket guide. All this part is the design element of the pocket guide, so it's all of this in the book. Okay? For you in first year, it's not necessary to learn everything of this, but I advise you to read this because it's very important for your professional culture as an engineer. Okay? You have some question on this? Yes?
What are the pages of the book?
This book?
Yeah, what are the pages?
The pages I will give you on espace. Okay? But is all the parts on design element is always the last one. Yes? We'll see an example of that. I have an example here or not? No. Yes, I have one. Okay. Here I will realize between the white part and the yellow a revolute joint. Just one rotation between them. I can realize this by direct contact between the two parts, or indirect. I will use a ball bearing. So a joint between the yellow part and the white one, but without a direct contact. I have an intermediate part to realize this contact. Here, a ball bearing. Okay? Yes?
How do you know the symbol by both or well?
Sorry?
How do you know the piece is assembled by both or by well?
You will see it on the drawing, on the technical drawing. Is what we will see today. Okay? So first, a complete joint. Okay? For a complete joint, you remove all the degree of freedom. Okay? Reminder of the previous lesson. Okay? The symbol of the kinematic diagram of a complete joint. Okay? It's just connection between the link. Zero compression, zero rotation. Okay? To realize a complete joint, we have two steps. First one is relative position. We'll put the parts in position each other. Okay? So we'll stop the movement between the parts. Okay? Second step is maintain in position. I will exert an effort. I will use extra parts to fix the position between the two parts. Okay? For the first step, relative in position. Okay? Also here, I have two technological functions for this. Okay? For this, we need precise surface. Okay? Precise contact. You remember, in kinematic analysis, we consider that the contact, the surface, are perfect. Okay? Two main categories of solution. Okay? The first one, I will using flat surfaces and pins or the wall. Okay? Don't worry, I will explain just after what are pins and the wall. Second solution, with using a cylindrical surface plus a rotation stop and also in general a translation stop. Okay? Example of these two main solutions. Okay, when I use flat surfaces and pin and door. Okay, if I use okay. If I use two flat surfaces, okay, between my hand and the box, here I create a planar joint. Okay, so here with the contact with the two parts, I have only 3 degrees of freedom. One translation, one second translation, and one rotation. Okay? Planar contact, 3 degrees of freedom. Okay? So here, when I realize a planar contact between two parts, I remove 3 degrees of freedom. This rotation is not possible. Okay? And I rotate one part, the second rotate also. Okay? The same for this, and the same for this translation. Okay? So now I will use this flat surface, okay? And I will add a pin or the wall to remove the rest of the contact. Okay? So a pin or the wall is a cylindrical part, like this, for example. Yeah, it's a split pin. Okay? An elastic pin, sorry. Okay? So we'll use this between my two parts. The first one, like this, will stop the two translations. Okay, remainder, planar contact, one translation, second translation, one rotation. I add between these two planar contacts the pin, okay, and like this I stop one translation, second rotation. Okay, the only movement possible here is one rotation. Okay, if I add a second pin, okay, small one here, for example. Okay, here I will stop the rotation between the two pins. Okay, so flat surface plus a minimum of 2 pins or the wall. Okay, I realize a complete joint. Okay, is the relative position of a complete joint. Okay, it's okay for you? Here, the objective is to remove all the degree of freedom of the part. Second solution, using cylindrical surfaces and rotation stop. Okay. When I realize a cylindrical contact, okay, so a shaft inside of ball. Here I have only one rotation and one translation. Okay, this means I remove 4 degrees of freedom. Okay, this rotation is not permitted. This one also, and the 2 translations are not permitted also. Okay, so here I remove 4 degrees of freedom. To realize a complete joint, I need to remove the 2/1. First, I will use a shoulder or a translation stop, okay, to fix the position and to stop the translation between the two parts. Second, a rotation stop to stop the rotation between the two cylindrical parts. Okay. So, different example. We'll see after all the example to rotation stop. Can use key, I can use clean. I have a lot of solutions for this, also for translation stop. Okay? What is important for you is to think that a complete joint is to remove all the degree of freedom, the 6 degrees of freedom between two parts. So I need to stop all the movement. Okay? When it's realized, I have to maintain position is to avoid the part to move. Okay? Is it clear for you? Do you have some question? So now we'll see for complete joint all the solutions to maintain in position. Okay? For you, it's important to learn all of this because when you will study a kinematic diagram or a technical drawing, you need to identify the different group of parts with the same movement. It means all the parts with a complete joint between them. Okay? So we'll identify the technological function to realize the complete joint. And you will see here, not all, but a very important number of technological functions for this. Okay? So, we will consider that to choose the way to maintain position the two parts, I need to consider the effort between the two parts. Okay? I will fix the main important effort. Okay? Main solutions for this, I can realize a permanent joint, okay, is an undemountable joint by rifting, welding, adhesion. Okay, we'll see all the examples after. I can use threaded element. Okay, remember all the second session. All the threaded elements, screw, nuts, etc. Okay. I can use all the family of pins, cylindrical, conical, fluted, elastic, split pin, etc. Okay. I can also use find function by adherence. Okay. It's solution by deformation, pinching, or tangent tampon. okay, or press fitting. You will see all the solution now. For the permanent joint, okay, first one, welding. Okay, I will weld two parts together. Okay, I will fix the part. Okay, indication on a technical drawing. So welding is for metal part. Okay, I will have between two parts weld. Okay, I will have a small triangle that indicates the welding between them. Okay, it's very used for all the mechanical frame. Okay, for example, body of a car, all the parts of the car are welded. Okay, all the structure of your table are welded here. Okay, if you look on your table, you have here the welding mark between the different tubes of the table. Okay. Second solution, rifting. Okay. To fix two parts by rifting, first we need to drill the part and to align the drilling hole. Okay. And we'll add a rivet between these two parts. Okay, it's a cylindrical part. Okay. And we will have on one side a shoulder, and the other side is just the cylindrical part. And then we will deform, will modify the shape of this part, okay, to realize a complete joint between them. Okay, here's the example. Here you see the rivet, the first rivet in red is before deformation. Okay, we deform it by a matrix and realize a complete joint between the different parts. Okay, if you want to disassemble two parts by riveting, we need to break the rivet. Okay. Last solution, adhesion. Okay, we'll add an adhesion element, glue or something else. Okay, to fix two parts together. Okay. Adhesion is more and more used in industrial using. Okay. For example, 50 years ago, assembly of plane are by riveting. Okay. You see on the aluminum part of plane, you have all the small rivets. Okay. Now, between 50 to 60% of the parts of the external part of the plane are gluing. Okay. Next solution to maintain in position. Okay. Before, no question on welding, rifting, or adhesion. Okay. So now all the solution with threaded elements. Okay. So we'll use bolt, screw, etc. First example, two parts, one with a ball, a hole, one with a threaded hole. Okay. And we will assemble the two parts together. Part A and B will be assembled by a screw. We have a lot of different screws. I have just some model here. Okay. In general, different screw by the diameter, the length, and the head of the screw. Okay, in function of the use you want. Okay. It's possible also to use two drilling parts and add a nut. Okay. You can have different example of nut. Okay. And you will fix, it's not the good side, but we will fix the two parts A and B between the screw and the nut. Tighten the two parts together. Okay. Or we can use screw or threaded element to realize the pressure between the two parts. Okay. Here we'll fix this part in the middle, inside the C-shaped part. Okay. And we'll use the press screw. Okay. To add an effort between the two parts and to fix the position of them, to maintain the position between the two parts. Okay? Or last example, the use of a stud. Okay? A stud is almost like a screw, okay, but without head. We'll fix the stud inside the first pair, okay? The second part, so in this part we have the threaded hole, okay? The second part is only drilled, and we use the nuts between them, okay? Be careful for all the solution, okay? You see here, part B is threaded. Part A is just drilled, but the diameter of the hole in the part A is bigger than the size of the screw. Okay? We have space here to permit the position, to take the position of the screw. Okay? It's why we never use screw to relative position between parts. We prefer to use pin because size of a pin is more precise. Okay? The screws are just here to maintain in position. Okay? It's the same here. Okay, we'll use a nut and a screw. A and B are drilled, and the diameter of the hole inside A and B are bigger than the diameter of the screw. Okay? With a small space, we see here between the diameter of the screw and the diameter of the hole on the part. Okay? The same here. The first part here is threaded, so you have the technical drawing of a threaded hole. Okay? But the second part at the top is just drilled with a bigger diameter of hole than the screw. Okay? I give you the part. Okay? So, with threaded elements, I had to use some washer. Okay? We have different use of the washer. First one is to increase the surface of contact between the parts. Okay? Second use is all the lock washer is to avoid the unscrew of the screw of the threaded element. Okay? So, example of a standard washer. Okay? Here I just increase the surface of contact between the different parts. Okay? Second, the lock washer. Okay? Here, when I will tighten the different parts, I will reduce the thickness of the washer. Okay? And the sharp edge of the washer will stop the rotation of the nut or the screw. Okay? The same with the first one, the grower. Okay, like this. We have a groove inside of the washer. Okay, and with this groove, we have two sharpened edges. Okay, that will stop the rotation of the screw or of the nut. Okay. This is for the washer. Another example, 7 lock nut. We'll use 2 nuts, one beyond the other one. The second one is named a lock nut, and it will stop the rotation of the first one. Okay? Solution 8, lock nut with lock washer. Look at the technical drawing with not always, but for using of a ball bearing, we often use a lock nut. Okay, a lock nut is like this. Okay, now. If you only use the lock nut, it's a standard nut. But we will use the lock nut with a specific washer. Okay, this specific washer of this particular shape. Okay, you see on this we have an important number of small rectangle like this. Okay. In the middle, we have only one. Okay, at the interior of the diameter. This tip will be put inside a groove, okay, of the shaft. Like this, we stop the rotation of the washer on the shaft. Okay. This one is represented at the bottom of the technical drawing. Okay. And you will screw after the lock nut, and on the nut you will see you have also 4 different grooves. Okay. So we'll tighten this, and it will stop the rotation of the nut. One groove of the nut in front of the tip of the washer. And we will fold the tip of the washer inside the groove of the nut. Okay? Like this, we'll stop the rotation of the nut because the rotation of the washer is already stopped. Okay? If you see on this drawing here, okay, okay, you see here in black is the washer. Okay, here this square with a cross is the normalized representation of a ball bearing. Okay, here we have the shaft. Inside of the shaft we have the groove. Okay, with a local section here. Inside of this groove we have in black the internal tip of the washer. Okay, and at the opposite, yes, and here also we have the tip fold inside of the nut. Okay, here it's just a representation of the washer. Okay. Solution 9 is what we call a castellated nut. Okay, I'm sorry, I don't have this part. Okay, castellated nut because of the shape of the nut. Okay, we'll add on this nut different shape like this, and inside of the shaft we'll drill a through hole inside of the shaft. Okay, when we screw the nut, we align the hole of the shaft with the shape of the nut. And between them, we'll put a split pin to stop the rotation of the nut. Okay? The split pin in red. Yeah, okay? Inside the shaft and the nut to stop the rotation of the nut. Okay? Solution 10, 11, 10, 11, and 12. Okay? Here's all the solution with screw. Okay? We see that we always use a pin, okay, for relative position to remove all the degree of freedom, and the screws are only here to maintain in position, to fix the position of the part. Okay, so here is the use of the dowel in the middle of the part with the screw in the middle. Okay. Last solution to stop rotation of the nut. Okay, we will use plate. It's like a specific washer. Okay, and we will fold one part of the plate on the body, on the frame of the mechanism, the other one on the nut. Okay, and this will stop the rotation of the nut. Okay. Do you have some question on this technological function? Okay. Now the use of the family of pins. Okay. A pin is a cylindrical part. Okay. One. Okay. Standard pin is like this. Okay, it's a small cylindrical part. Okay. In general, we have a chamfer on one side, a round on the other side. Okay, and we'll place this pin between two hollow parts. Okay, we can put it between two flat parts. Okay, to stop the movement. Okay, use of two pins to realize the complete joint. Okay, or also like the example between two cylindrical parts. Okay, one side of the pin have a chamfer to be able to facilitate the coming of the pin inside the hole. Okay, it's easier to put the pin if we have a chamfer. At the opposite, we have a round. Okay, you can use a hammer to hit the pin. Okay, a cylindrical pin just fix the position, but not maintain it. Okay, but we have different use of pin. Okay, we can use a conical pin. Okay, well, it's a pin with an angle. Okay, it's not cylindrical, it's conical. And like this, the diameter of the hole is smaller than the bigger diameter of the conical surface. Okay, like this will force the pin inside of the hole to maintain the position of the part. Okay. In the middle, the split pin. Okay, you will use it. It's a pin like this. We'll use it during technical workshop in Fab Lab. Maybe some of you have already used it. Okay. It's a pin with two legs. Okay. Now, the two legs of the pin. Okay. We put the pin inside the hole, and after we'll fold on each side the two legs of the pin to avoid the movement of the pin. Okay. In general, the legs are too long, so we cut them. We can use fluted pin, okay, or elastic pin. Here, I have example of elastic pin, okay. So it's a pin like this, okay. Well, it's like a tube, but with a groove on all the length, okay. The size of the pin is bigger than the size of the hole, okay. But we have an important chamfer, okay? And when we put the pin inside of the part, we'll close the groove to reduce the diameter of the pin. But because the metal of the pin is elastic, it will try to reopen inside the hole and maintain in position like this. Okay? Do you have some question on the pin? Okay. During technical workshop, you will use split pin for the fixation of the connecting rod inside the deformable finger. Okay. And we'll use cylindrical pin to fix the deformable finger inside the piston of the main body. Okay. All of you have had already one session of technical workshop or not? Okay. So we'll see all of this during technical workshop. Okay? What is important here is to see all the samples of technical drawing of the technological function to be able to read them on the technical drawing. Okay? You need to recognize them on the technical drawing. Okay? Solution by deformation, by adherence. Okay, you have two main solutions. Okay? So here we'll fix two cylindrical parts. One and two. Two is, for example, a shaft or a tube. Okay? And you will use a screw here to reduce the internal diameter of the part 1 to tighten this part around the shaft 2. Okay? All of you have already used this system. Where? On a bike. When you want to adjust the height of the seat, the system is this one. Okay? We'll deform the tube outside of the seat, okay, of the tube seat, okay, to fix the position. Okay? Second solution, the use of tangent tangent. The solution is almost the same, but we'll use intermediate part, tangent tangent. It's part with an important coefficient of adhesion. Okay? One is just drilled, the second one is threaded. Okay? So this one is threaded. You will tighten them, it means you reduce the space between these two tangent tangents to exert an effort on the internal part number 2. Okay? Is it good for you? Yes?
Can you re-explain? I didn't understand how the pinching works.
For the pinching, you think that here is the part number 2. It's a shaft in section. Okay? Around you will put the part like this. Here you have space. Okay? So we will tighten this. Okay? You will close this part to be like this by a screw in the middle, plus a nut or a screw inside a threaded hole. Here it's a screw inside a threaded hole. Okay? So by reducing the space, we'll exert an effort, concentric effort all around the part number 2 in the middle, the yellow one here, to maintain the position between the blue one and the yellow one. Okay? Is it okay for you for this solution? Okay. Last one, press fitting. Okay. Yeah, it's just a small introduction on press fitting because we'll see more in details press fitting at the second semester. Okay. Press fitting is the fact to put a bigger part, a bigger cylindrical part, inside a smaller hole. Okay? So, just like this, okay, you have a ball with a diameter D1, part 1, a shaft, part 2, with a diameter D2, okay? And the diameter of the shaft is bigger than the diameter of the ball, okay? We'll exert an important effort to put 2 inside the part 1. It's also possible to hit part 1 to have a dilatation, or to freeze part 2 to have retractation, okay? To be able to put 2 inside 1, and like this you realize a complete joint between the 2 parts, okay? When we say that the diameter of the shaft is bigger than the diameter of the bore, is not a difference of 1 millimeter. It's a difference of micrometer. Okay? Just some micrometer are sufficient to fix the position between 2 parts. Okay? For this, we'll see it on the second semester by the ISO system of assembly of 2 parts. Okay? Is it good for you? So, to realize a complete joint, we'll combine solution of relative position and solution to maintaining position. Okay. So the main example with flat surface, I will assemble two parts with flat surface. Okay. I will use two pins to stop all the movement between the two parts. Okay. One here, the other one in the middle here. Okay. You see in section the pin here. Okay. And after we'll use screw here, for example, 3 screws to maintain in position the two parts together, to tighten the parts together. And like this, I realize a complete joint. Okay? With cylindrical contact, okay? So here I have the cylindrical contact, so I need to stop translation and rotation. To stop the rotation, I will use a key. We'll see after definition of key. Okay? The key will stop the rotation. Okay? On one side, we have a shoulder at the left. We have a shoulder that stops the movement between the two parts. And at the opposite, to tighten the parts together, we'll use a washer plus a screw inside the middle of the shaft. And like this, we realize a complete joint. Okay? It's sometimes possible to realize relative position and maintaining position in only one movement, with only one part. Okay? Is when you use elastic pin. Okay? Here we'll directly stop all the movement. Okay, we have a cylindrical contact. The pin in the middle will stop rotation and translation. Okay, and because it's an elastic pin, the effort of the pin is sufficient to maintain position with support. Okay, is it clear for you for the complete joint? Yeah. So now sliding joint or giving in translation. Okay? So here we'll realize a sliding joint. Okay? So reminder of the previous session. Okay? Kinematic symbol, kinematic diagram of a sliding joint, and the movement in a sliding joint are only one translation. Okay? 0 rotation, and only one translation. Okay? Well, a lot of different solutions to realize a sliding joint. Okay? And we'll choose the solution in function of the cost, size, the effort, etc., etc. The use, main important, the use. Okay? And we'll see now the different solutions to realize a sliding joint. Okay, first we can use cylindrical surface plus a rotation stop. Okay, think about this. When I realize a cylindrical joint, okay, so a cylindrical part inside a cylindrical hole, here I remove 4 degrees of freedom. Okay, I only have one transition and one rotation. If I stop this rotation, I only have the transition, so a sliding joint. Okay? So to realize a prismatic joint, a sliding joint, I can use a cylindrical contact plus a rotation stop. Okay? First use of a rotation stop, the free key. Okay? A key, it's a very small part. I have one sample somewhere. No, I forget them. Sorry, I forget them, or I lose them. So the key is the small part, the small rectangular part in the middle. Okay? We'll put the key, okay? So the key is the part in red. Okay? We'll put the key on the shaft inside the key seat. Okay? Like this, the key can't move inside the shaft. Okay? And this key will be put inside a groove of the ball. Okay? And the flat surface, the flat lateral surface of the key will stop the rotation between the ball and the shaft. Okay? We have different forms of key, A, B, C, and wood cross key. Okay? The most common use is the A, and when we have inverted effort, we can use the root rod. Okay? I'm so sorry for losing my sample. Okay. I'll bring you another sample next time. Okay? It's okay for you for the key? Okay? You see with this diagram, I put the key inside the key seat. So like this, the key is fixed inside of the shaft. And after, the two flat surfaces of the shaft would be inside the groove, and these two grooves stop the transition. Okay? I can draw you the technical ring in the opposite direction. Okay? On the shaft is like this, with the key seat. Okay? Inside we put the key. Okay? And outside we have the ball. Inside of the ball we have a groove. Okay? And like this, on these two contacts here, we stop the rotation between the two parts. We only have transition in this direction. Okay? It's good for free key. Okay? We can use also some screw inside the slot to stop the rotation. So, inside of the shaft we'll have a groove, almost like a key seat. Okay? Inside the ball we have a threaded hole. Inside this threaded hole we'll screw a small screw with a specific point. Okay? And this point will be inside of the groove of the shaft to stop the rotation of the shaft. Okay? Next solution, fluted shaft, okay, is almost like key, but here, because of important effort, I directly machining the shaft to have this particular shape, okay, like this. Okay, but here is like we have 6 keys, but it's directly machining, manufacturing inside of the shaft. Okay, so we have here an example here, and also between these two parts. Okay, here and here, we have the fluted shaft here. I have the translation of the part without the rotation. Okay, I will show you this part after. It's another example. Okay. The next solution is a particular one. Okay, is an addition of cylindrical joint. Okay. If you use one cylindrical joint, we stop 4 degrees of freedom. Okay. If we add a second cylindrical joint and link the part together, the second cylindrical joint will stop the rotation of the first one. Okay, the example like this. Okay, a cylindrical joint here. Okay, but I have a second cylindrical joint. Okay, the second cylindrical joint will be used to stop the rotation of the first one. Okay, to have the functionment of a system like this, the precision of the parts is very important. Okay, view in 3D. Okay, to be sure to be able to assemble the second part with the two bore on the two cylinders. Okay, the dimension between the two axes of the cylinder need to be exactly the same as the dimension between the two axes of the bore. Okay. For this, in general, we need to reduce the friction of contact between the parts. Okay. So to realize a passive resistance solution for a sliding joint, we have different solutions. First one is the linear bearing. Okay, it's a part like this. Okay, and inside this part we have some small balls with a system of circulation of the ball inside of the part that will reduce the friction between the two parts. Okay, and if we use this, we can add two of this solution to realize the double stem of the previous one. Okay, when you look this part, this one is cut to show you the middle of the part. In general, it's totally closed. Okay, and you can see the movement of the ball inside of this, the circulation of the ball. Okay. Next solution will directly use the shape. Okay, so think that at the beginning we use cylindrical surface plus a rotation stop. Here we'll use directly a shape that stops all the movement except this transition. So the first one is the T form. Okay, you have two parts, 0 and 1. Shape of 0 is a T. Okay, we have the same shape inside 1. Okay, plus additional part screw on 1. Okay, and part 0 will slide perpendicularly to the screen inside 1. Okay. For this, we can also have some passive resistance solution. Okay, you have directly inside this a T shape. Part in the middle have exactly the same shape. Okay, here is the plastic material that reduces the friction, and you will realize a sliding joint. Okay, internal or external. Okay, have also the T shape, and here small part of plastic that reduces the friction between the two parts. Okay. The same with a square. Okay. With a square, I can stop the rotation. Okay. No possible rotation between two square parts. Okay. So here I realize a sliding joint, direction of the movement perpendicular to the screen. Okay, the square part in the middle, slide inside the second one. Okay. Last one is the dovetail form. Okay. In precision mechanics is the most common use. Okay. because we have a specific angle, okay? So this is the solution. We have a specific angle that reduces all the space between the parts. And we can add another part here to adjust this space. And we have just the translation also perpendicular to the screen. Okay? If you look on the turning machine of the Fab Lab, you will see that the movement of the tools, okay, on the Fab Lab is realized by dovetail. Okay? Why dovetail? Because we have exactly the shape of the dovetail. Okay? It's good for you? You have some question on this? No? We have also a solution with prismatic surface to reduce the friction. Okay? So the one with plastic, okay? Here is the shape, the surface of contact of plastic that reduces the friction, okay? Or we have another solution, solution with rolling elements, okay? So here we'll have 4 small wheels with a ball bearing inside that reduce the friction of the rotation of this part, of this wheel. And this wheel will roll, will turn outside of the second part. And like this, I will reduce the friction, and I have a very precise movement. So the shape, okay, you see. At the opposite, I have the trolley with the 4 wheels. Inside of the wheel, I have a ball bearing that reduces the friction of rotation. Okay? And I can assemble them to realize a sliding joint. Okay? Without friction. Be careful, this one is easy. Okay? Is it good for you? Yes. Do you have some question on the guiding in transition, realization of the sliding joint? Yes.
Wouldn't spline be perfect?
Please.
Wouldn't spline be perfect for avoiding in translation?
Sorry, I did.
Wouldn't spline be perfect for translation?
We consider that all the surface, all the contact are perfect, okay, because of the kinematic analysis. But in fact, we need small space, okay, to permit the assembly of the different parts, okay. Or I can show you this. I will see it with the revolute joint. It's okay for you. It will be better. I have more example. Okay, answer almost at your question, or okay, we'll see with revolute 1. Okay, it's good for sliding joint. So now, revolute or turning joint. Okay, so guiding in rotation. Okay, guiding in rotation. I will remove 5 degrees of freedom. Okay, and I leave only 1 rotation. Okay, remainder kinematic symbol of the turning joint. Okay, turning or revolute joint is exactly the same. Okay, 0 translation, 1 rotation. Okay. How to realize this? Okay. So to realize a revolute joint, I need a cylindrical contact plus a translation stop. Okay. So when I realize a cylindrical joint, okay, I remove 4 degrees of freedom. I only have one transition and one rotation. If I stop this transition, I realize the revolute joint. Okay? So first solution is to realize a direct contact. Okay? I directly have the contact between two parts, two cylindrical parts, with a direct contact to stop the transition to realize a revolute joint. Okay? Is the joint you have, for example, between a door and the wall, or a window with the wall. Okay? The door can just turn, or the window can just turn. Okay? I have a direct contact. Okay? And the weight of the door or of the window will stop the transition. Okay? I can use, in fact, in mechanical design, for revolute joints, I need to reduce the friction. So I need a low resistance solution. First solution is the use of plain bearing. Okay? The plain bearing is a small part, a small cylindrical part. It's an intermediate part. So like this, I realize an indirect contact between the parts. Okay? And this part will reduce the friction between the different parts. Okay? In general, this part is in copper, like this. Okay? We'll realize this part by an agglomeration of powder of copper. Okay? So like this, if you look the part, you have very small hole inside of this part. And inside this hole, we'll add oil to lubricate the movement between the different parts. Okay? So we can have solid sleeve bushing. We call also that part a bush. Okay? So have a bushing. Okay? That permits the rotation of the part. Or the second one is a flange. Okay, a flange one. So we have like a small shoulder on the bush. Okay? And we can use this bush here to stop also the transition. Okay? On the shoulder. Okay? Most common use in copper, but you find also them in plastic. Okay? I review the part. It's okay for bushing. Okay? So solution of plain bearing. Next solution, rolling element bearing. Okay? Most common is ball bearing. But we'll see that we have different elements. Okay? So the standard one is a ball bearing. Okay? We will find different components inside the ball bearing. The inner ring will be the ring in contact with the shaft. Outside, the outer ring in contact with the ball. And between these two parts, we have all the ball of the ball bearing. Okay? Like this. Okay? Now, in the inside, inner ring, in the middle, the ball, outside, outer ring. Okay? And well, the rotation must be like this. Okay? I have the rotation between. I have a very important number of solution pairs of solution with rolling element bearing. Okay? We can find ball bearing for all the different use you can find. Okay? Okay. So the most common one is the ball bearing. Okay? Example like this. On this ball bearing, we can add like this some sealing function here in black to protect the ball of the bearing. Okay, it's not necessary. This example, if you don't use ball, you can use cylindrical. Okay, with or with not inner ring. Okay, so here the rolling element is a small cylinder. Okay, so it's possible to find them with inner ring, but it's not necessary. Okay, we can have with conical element like this. Okay, here is directly a small conical surface of contact. Okay, to create the rotation. So here it's for important axial effort to stop them. We can find roller bearing with small needle. Okay, so very small cylinder. We can find plate bearing. Okay, we have ball like this, two ring. Okay, and here you have a rotation in this direction. Okay, is to create a rotation between two plates, for example. Okay. You can have ball bearing with two lines of ball. Okay, and when we have a ball bearing like this, we don't realize a turning joint, but we realize a spherical joint because we have all the rotations. We have three rotations here. First one, second, and third. Okay? So for the first year, you are to recognize ball bearing inside a drawing, inside a technical drawing. Okay? For this, look inside the technical pocket guide. You will see in ball bearing. Okay, you will find all the explanation about ball bearing, and you will see all the different models of ball bearing. Okay, I have an important number of pages on ball bearing. Everything is here. Important, inside the technical pocket guide, you have the normalized representation of each ball bearing, each bearing. Okay, so look at this to be able to recognize them on a technical drawing. Okay? Important points for ball bearing. We never use a single ball bearing. Okay? You see in the previous example, here I use two ball bearings. Okay? If I use only one, it's not correct because I have some small space inside of the bearing and I don't realize a truly revolute joint. Please. Okay? So I need to use two ball bearings, but inside your kinematic analysis, two ball bearings is equivalent to one turning joint. Okay? Be careful at this. Okay? In mechanical design, we have a lot of rules to be able to assemble ball bearing or rolling element bearing. Okay? All that rules are subject of mechanical design in second year. Okay? First year, you just have to be able to identify them on a technical drawing. Okay? You see that we have seen three different solutions to realize a revolute joint. Okay? Direct contact, plane bearing, and rolling element bearing. But for all that solution, I use a cylindrical contact plus a translation stop. So in fact, to realize a revolute joint, we need to know the solution to stop in translation. What we'll see just now. Okay? Okay, to explain. So first solution to stop the translation, a shoulder. Okay? Between two cylindrical parts, I will use a shoulder. A shoulder is a difference of diameter on the shaft. Okay? And like this, I have a contact here that stops the translation of the part with the second one. Okay? First solution, a shoulder. I can use a split pin. Okay? I will add a pin, a split pin at the end of the shaft inside the hole, and like this I stop the translation. So the complete solution is shoulder plus split pin. Okay? Shoulder on one side, split pin at the opposite. Like this, I stop the translation of this part on the shaft. I have only the rotation like this. Okay? I can use threaded elements. Okay? So I will use the washer. Okay? Like this, I have an important surface of contact plus a screw inside a threaded hole of the shaft. And this stops the translation between the two parts. Here we have contact between the part and the washer that stops the translation. Okay? At the opposite, I can use a second washer or a shoulder, etc. Okay? I can also use the set screw. Okay, remember for guiding in translation, I use on the shaft a groove parallel to the axis. Here I will use a revolute groove around the shaft. The set screw will be inside this groove. Okay, and like this we stop the transition. Okay, you see that the shaft in the middle can slide because of the screw. Okay. This solution is the one used on the robot gripper of the technical workshop inside the Fab Lab. Okay. When you want to stop the translation of the main screw inside of the main body, okay. Inside the main body, we have realized a small hole plus the shape of a nut to be able to screw the M3 screw, okay? And inside of the main screw, realize on the manual turning machine of the Fab Lab, we realize a circular groove to put the head of the screw inside it. Okay? Retaining ring, okay? We have different use of retaining ring, internal or external. A retaining ring, it's a small part like this, okay? This one is an external one. Okay, different size of external ring or internal retaining ring, okay? So we put the ring inside of a small groove, and the flat surface of the ring will stop by a direct contact the translation. Okay, here is an example of an external retaining ring. It's put at the external side of the shaft with an internal retaining ring. We'll put it inside a groove of the bore. Okay. And we'll put it inside of the bore. An internal rotating ring is a solution to stop the transition of the nut inside of the piston of your robot gripper in the technical workshop. Okay? Be careful at the representation of the rotating ring. In general, we represent it in section. Okay? And you see the rotating ring is here. At the top, we have hatching inside of the rectangle of the rotating ring, but it's not the case here, because we always represent the rotating ring like this. So think that if we cut the rotating ring in the middle, at the top we are inside of the rotating ring, so we have material, so we have hatching on the section plan, but here it's empty, so we have nothing, we just see the external shape of the rotating ring. Is it okay for the rotating ring? Okay. Be careful at this, because it's very important use in mechanical conception, mechanical drawing. Okay. And it's a very small part, so it's often that you don't see the rotating ring. Okay. Do you have some question on this? Okay, so next solution, the elastic pin. Okay. So with the elastic pin, we'll directly put the elastic pin between the part and realize the transition stop. Okay. So here in the shaft we have the hole. In an external part, well, the second hole. Like this, we realize a complete joint between this part and the shaft. Okay. And we stop the transition here. It's almost like a shoulder, okay? But here it's a demountable one, because it's not possible to put shoulder on each side, okay? Because you can't assemble the part. So we'll add this solution to realize the complete joint, okay? To realize the turning joint, the transition stop. Is it okay for you? Okay, I forget to show you some assemble of ball bearing. Okay, so I have always two ball bearing. Okay, the shaft in the middle, and you have different solutions to stop the transition. So, in general, outside, we have a shoulder plus a cover. The cover is screw inside the main body that permits a contact on the outer ring. Okay? Inside is not necessary to stop all the movements. Okay? We can have shoulder or a spacer. Spacer is the blue part. Okay? That permits to fix the distance between the two inner rings. Okay? You can see also an example like this. At the black part is a seal. If we have oil inside of this, we'll use a seal like this to stop the oil to go out. Okay? First example. Okay? Second one. Okay, it's the same, this one. No, it's not the same because, no, it's not complete. Second one, okay, here I will use an adhesion. Here I will glue a cover, okay, to stop the inner ring. In blue is an external spacer, okay, and I have shoulder on the shaft to permit the rotation. Okay. Do you have some question on this? Okay? So now you are able to read the technical drawing. Yes? So I will give you an exercise. What are you doing?
I'm going to the bathroom.
You can ask me maybe.
I'm going to the bathroom.
No. If you ask, well, yes, but first ask me, no. So your first tutorial is about air compressor. Okay? I give you the technical drawing of this mechanism. Okay? It's a very small one, only 19 parts. Okay? With this, you have to follow the way of use of the kinematic analysis. Okay? First step, identify the group of parts. Okay? Second step, identify the joint between the different group of parts. Okay? And last step, draw the kinematic diagram. Okay? I leave you to read this document. I will print someone to give them to you. Okay? Okay, I will print the document. I'll come back in 5 minutes. Start of this, and during this time, you can go to the bathroom.
On l'a dit maintenant. Vous me tenez ou pas?
Okay, everyone, stop the document. Okay.
On est d'accord que le truc à jouer, il faut faire les trucs.
Okay, I leave you 5 minutes maximum to read this drawing. Okay. After I will give you some explanation, and I will help you with some technological questions. Okay. You need to try to identify the standard component, the standard part. So for this, you have the nomenclature to help you. Okay. And with the nomenclature, you can find the use of the different parts. Okay? Advice: to identify the group of parts, the best is to directly add color on the technical drawing. Okay? That's why you need to use color pencil. Okay? 5 minutes for this. Okay, if you want, I add the technical drawing on espace also.
Si ça ne bouge pas, le truc est plutôt facile. Mais d'accord, tu fais un truc comme ça. Si ça ne bouge pas, genre,
I forgot one example. Use of a retaining ring to stop the translation. Okay, here on these two parts, you have two retaining rings, one on one side, one on the opposite, to stop the translation. And also, I find them simple. Okay, 5 minutes. I explain the functionment of this system. This system is an air compressor. Okay. So here, the electric motor that creates the movement is not drawn on this drawing. Okay. The electric motor will be connected by belt, pulley, and belt. Okay. Here you have the pulley. Okay. So the input parameter of your system here is the rotation of that pulley. Okay. At the top, okay, you have a piston here, okay, with a chamber, okay, and at the top, the piston is here, the chamber is here, and here you have the air valve box, okay. So you have an inlet valve and an outlet valve. When the piston goes down, okay, the inlet of the chamber, okay, and when the piston goes up, okay, the air goes outlet with the pressure. Principle of an air compressor. Okay, so for the kinematic analysis, limit of boundary will limit our study at this mechanism, this compressor. Okay, so only this drawing. Okay, we don't consider the electric motor or the rest. Okay, inlet parameter is the rotation of the pulley parts 10. Okay, outlet parameter, okay, is the translation of the piston. Okay. To help you to read this drawing, you need to ask you the use of different parts. Okay? I list for you the parts. Okay? So look at the part 7. Bush. First question. How many bush 7 you find on this technical drawing? Yes. You see? So first one is here. So the black part indicated by 0, 7. The second one is at the opposite. Okay. So first 7 is here. Okay. Second 7 is here. Okay. So what is the use of the bush 7? Use of a bush guiding in rotation. Okay. So think that if you have a part to guide in rotation, you will have, in general, a revolute joint. Okay? But to have a revolute joint, you need also some translation stop. Okay? Second part, part 9. Okay? 9 is the key. Okay? Is here, in the middle of the pulley. Okay? Use of a key, rotation stop. Okay, so the key 9 will stop the rotation between the pulley here and the shaft, the crankshaft here. Okay, 9 is here. Okay, and we stop by this key the rotation of the pulley with the shaft. Okay. Part 12, Castellani's nut. Okay, part 12 is at the opposite. Is here. Okay, at the opposite of the crankshaft. Use of a nut like this is the translation stop. Okay, you see, all the answers of that question are found inside the previous course of today. Okay? An elementary element, a standard component, is always used for the same. Okay? A key, rotation stop. A bush, getting in rotation. A nut, maintaining position, translation stop. You need to learn that. Okay? The split pin, nut rotation stop. Okay, we'll put the split pin inside of the Castellani nut. Okay, and this split pin will stop the rotation of the nut. So use of 15 is a nut rotation stop. 14, okay, 14 is here, is in contact with the pulley 10. Okay, so it's also a translation stop. Okay, and the second nut, okay, it's a lock nut. You have an assembly with 2 nuts. So the second nut is a nut rotation stop. Last part, part 19. Okay, it's a rotating ring. Okay, it's here inside of the piston. You have 2 internal rotating rings. Okay, I will show you here. Okay, 19 is here, so the first rotating ring is here. The second one is here. Okay, use of a rotating ring is always the same, is a transition stop. Okay. To help you, do you in the use of this mechanism, the functionment of this mechanism. You can ask you why we have drawn shape like this, okay, the fin on the part 2. What do you think about this? Yes. Yes, exactly. We'll increase the surface of contact, okay, to refresh the cylinder. Okay, the movement, the repetitive movement of the piston inside of the part 2 will generate heat, okay, and to refresh the cylinder will increase the surface of contact with the external air of the mechanism. Okay? More complicated. What is the function of the slot on the part 3? Okay, we have 2 slots here on the part 3. What is the function of the slot? Okay, on the technical drawing, you see the slots are here on the top view, or on the 3D view, you can see the slot here. Well, here you see one slot, the second one, another one here, another one here, etc. All around part 3, we have slots. So, what is the use of the slot? Yes? Not exactly. No idea. Yes. 3 is screw inside part 1. How we know that? Because we have here the representation of a threaded element. Okay? Oh, so inside 1, we have a threaded hole. Part 3 have an external threaded cylinder. And to assemble these 2 parts, we will screw 3 inside 1. And to be able to screw 3, we need all that stuff to be able to put a spanner, a wrench, to tighten 3 inside 1. Okay? It's good? I leave you time to find the group of parts. Okay? So now, with all of this, you have to identify the group of parts. Advice for this, just work on this view, okay? This one on the screen, okay? Use pencil color to identify the group or the non-movement relationship graph, okay? To identify the different groups. For this example, you need to find 4 different groups. Okay? The shaft is up here. Yes, inside of it. No. No, we have a rotation. Yes, but we have to without the same movement. Yes, but we have a different technique. Yeah, on the shot, just turn around this side. Okay, but this shot, turn around up the action movement because of the technique. Like, and that one. It's up with them.
Okay, so we can't like and another question, which one was in which were the 17 yes, because they are
You're welcome.
what way to go? Ça n'a rien à voir. Ah oui, ouais, mais franchement, c'est pas trop. Oui, oui, c'est ça. Oui, donc le fait, il est tout ça.
Okay, please. We haven't got the time to finish this exercise. Okay? So we will have to finish it at home for next time before correction. But to help you, okay? Just wait, it's not finished. I will show you the movement of the air compressor. Okay? You see the air compressor like this. In color, and when we have the rotation of the tray transmitted at the crankshaft will transmit the movement at the connecting one and create the vertical displacement of the piston. Okay? So for next time, you have to identify the 4 different groups. Okay? With this, it's easy. You have already 4 colors. Okay? To identify the group, non-movement relationship graph plus coloring of the technical drawing. Second step, graph of link. Identify the different joints between the different group of parts. Okay? And to finish, draw the kinematic diagram by using the normalized symbol for the different joints. Okay? Yes? Which one? You have already the technical drawing? Please. You speak about this one or previous one? You have to finish. I don't put the instruction on the start. Follow the technical solution for kinematic analysis. So, identification of group, non-movement relationship graph and coloring of the technical drawing, graph of link to identify the different joints, draw the kinematic diagram. Okay? Thank you for today, and see you next time. Goodbye. Bye.